Now let's see what's going to happen with our solution if nu is integer. So now there is no need for branch cut, and now the integrand has a pole of the n+1 order at the origin. So, and this is also always very good, because in this case we can choose the contour in terms of a closed loop circling around this pole. Obviously our v function, which as you remember is as follows, also becomes single valued, and it's assumed identical values if we use the closed loop contour. Right, so this time this integral can be actually computed exactly because it has this n+1 order pole, and the whole computation is reduced to the nth derivative. But probably it's easier to compute it if we introduce the suitable change of variables. For example, here in the exponent, we clearly can detach the full square as follows. So let's introduce the new variable, t minus 2y equals minus 2s. In this case, so the initial contour circles around the origin, but when t equals 0, then s variable is going to be equal to y. So in our new complex plane of complex variable s, the contour will be a closed circle, but around the y point. And since we have this minus sign, it will circle around in clockwise direction. So now our integrand becomes phi equals to this new contour. And so we detach the full square, so we can factor out e to y squared. And under the integral, we'll simply have e to minus s squared ds, 2ds. Okay, let's put here negative sign. 2ds divided by s minus y times n+1, 2 to n+1 multiplied by -1 to n+1. So in the end, we'll have a -1 to n divided by 2 to n, and the closed contour integral around point s equals y, e to minus s squared ds over s minus y to n+1. And let's hope that this solution will give us the bounded answer, this integral. We compute it. So it's n+1's order pole. And the integral is just 2 pi I divided by n factorial and the nth derivative taken at point s equals y. So, and sorry, I forgot, I dropped actually e to y squared term here. And this derivative is simply turned into the derivative with respect to y, because it's taken at s equals y point. So, and the final answer for this integral so now let's study the structure of this expression in the curly brackets. For example, let's even take the first derivative. So if n equals 1, then the first derivative will simply give us -2y multiplied by e to minus y squared. And this e to minus y squared will cancel with e to y squared, and we'll simply have negative 2y in these curly brackets. The same situation will repeat itself for n equals 2. So we'll have some kind of polynomial, this time of the second degree, because we'll have to differentiate twice this exponential, e2 minus y squared. But again, this second degree polynomial will be multiplied by this exponential. And this exponential will always cancel with the prefactor exponential. So this way, we come to the conclusion that their expression in the curly brackets is always an nth order polynomial. In fact, there is a special name for that kind of polynomials. They are called Hermite's polynomials. And they are defined as follows. It's basically the same kind of expression, but multiplied by this negative sign, negative 1 to n. So for integer n, we get the polynomial growth for our phi function. But this is OK, because our initial wave function is multiplied by this decaying exponential function. So finally, we get the bounded solution. And as you remember, our new parameter, which is now turned into n integer, was related to our initial energy parameter as follows. So 2 nu was equal to 2e divided by omega minus 1. So now nu became an integer. And as a result, our energy has become omega times n plus 1, 2n plus 1 divided by 2. So it's n plus 1/2. And everyone obviously recognizes the quantization of the energy level of their harmonic oscillator. So this is how the whole procedure worked. So let's actually recall our principal steps. First of all, we got rid of their quadratic coefficients in our equation by introducing the suitable ansatz in terms of the asymptotic solution of our simplified Schrödinger equation times new function of phi. And for this new function of phi, we reduced our original quadratic equations to the equation with linear coefficients and represented our phi function with this suitable contour integral. And then we studied the asymptotics of this contour integral for large positive and negative values of y, of our coordinate. And finally, we came to the conclusion that we can't construct the bounded solution for arbitrary values of our new parameter, which is the energy parameter for our equation. And then we needed to change drastically the structure of our solution of the analytical structure of our integrand. We changed this arbitrary new parameter or energy to the integer 1 to n. And this way, the whole picture of our solution changed entirely, and we arrived at the polynomial behavior for the exact polynomial behavior of our phi function. And this way, we constructed the bounded solution and get the correct energy levels for our harmonic oscillator.